Alrighty, as we look at example 7.2 today, you should see that the very first section of this, where the track and field athlete is throwing a hammer, you can see that these are exactly the same topics that we talked about in the first video. The source of the centripetal force when he's twirling this hammer around his head is the rope. The tension on the rope is what's causing the centripetal force. And so if you know the radius with which he's twirling it about his head, in other words, what the length of the rope would be, you know, with the mass of the object he is twirling, then you're pretty easily going to be able to calculate what the velocity of that object is just by using the centripetal force formula that we already talked about, the mv squared over r. So again, that's pretty much just a plug the numbers in, chug out the answer. And since we've already talked about those concepts, I'm not going to spend any more time on that particular problem. What I do want to spend some time on, though, is the second part of that example. And that's where we have a car going around a curve. And this one is, the concepts here are a little bit different. So I want to make sure that you understand the concepts. On a curve, obviously a curve is a piece of a circle, so you have circular motion. And you probably already know that if you try to take a curve too fast, whether you're in a car, whether you're on a bicycle, whether you're on a skateboard, you know that if you try to take it too fast, you're going to skid right off of the curve, and so that you can't go too fast on it. So what's causing the force on a car that's going around a curve? Well, what sorts of forces are acting on the car? Well, obviously there's going to be the weight of the car that's acting down. There's going to be the normal force, which is the road that's going to be pushing up on the car. The car doesn't have any vertical component of motion, so those two are going to balance out, be equal to one another as far as their magnitude. What else? What other kind of force would be acting there? Well, friction is the other source of the force, and friction, if you have something on a curve like that, is actually causing your centripetal force. So in this particular case, what I have to think about is the fact that the centripetal force is actually the same as the frictional force. Well, what do I know about frictional force? Well, I know that frictional force, from when we talked about this earlier, is the coefficient of friction times the normal force, right? Okay, that should look familiar to you. We know that the coefficient of friction for this particular vehicle, for the road, the car and the vehicle, is 0.34. So I know the coefficient of friction, and then I need to know the normal force. Well, what do I know about the normal force? I know that the normal force in magnitude is going to be equal to the magnitude of the weight. So therefore, that's also going to tell me that magnitude-wise, that would be equal to the coefficient of friction times the weight. Okay? I know that the weight is the same thing as the mass times the gravity. So, you know, again, I'm just substituting things that I already know to try to find an equation that I can actually use. So therefore, what that tells me is that the centripetal force is going to be equal to mu times the mass of the car times the gravity. Well, I kind of have a problem because I don't know what the mass of the car is. So what I can do is, okay, I'm going to solve this equation in terms of whatever the mass of the car is. So the centripetal force is going to be equal to 0.34. I don't know what the mass of the car is, but I know that gravity is 9.8 meters per second squared. Okay? So the centripetal force is then, when I multiply that out, is going to be 3.3 meters per second squared times the mass of the car. Now, the question is, how did that help me? Okay? Well, I do know another equation for centripetal force. I know that centripetal force can also be calculated mv squared over r. We've used that equation before. So if I set this equation equal to this, I should be able to solve because I know the velocity and I know the radius. So therefore, I'm going to take this down here and I'm going to plug it in. 3.3 meters per second squared times m. Now I want you to notice what happens. I have an m on this side and I have an m on this side, and so they cancel out. And so therefore, I know that 3.3 meters per second squared is equal to the velocity squared over the radius. Well, I know that the radius of curvature is 15.1 meters, so then I'm going to take v squared over 15.1 meters equals 3.3 meters per second squared. I'm going to multiply both sides by 15.1, and when I do that, I'm going to have v squared. So once you multiply this, you'll have meters squared per second squared. Then if you take the square root of both sides, then you're going to have meters per second, and the numbers work out so that you're going to get 7.1 meters per second. Okay, so that is the maximum velocity that the car can travel around the curve without skidding. Now, what this tells us is two very important principles that are true. First of all, if there's not enough friction, you're going to slide off. And so that's why, especially if you have wet roads or icy roads where your friction is going to be reduced, you have to slow down. So secondly, the mass of the vehicle does not make any difference when you're going around a curve. We saw that it completely cancels out here. And so it doesn't matter if you're driving an 18-wheeler or you're driving a motorcycle. It doesn't make a bit of difference because the velocity around that curve is going to be the same no matter what kind of vehicle it is that you're actually driving, okay? So this is a technique that we're going to be using several different times throughout the rest of the module, where I'm going to say, okay, I have, again, two equations, two unknowns, but if you have two equations and two unknowns, you can solve one for the other, and things are eventually going to cancel out. In this case, it's the mass that cancels out. And this is a trick that we will be using a little bit later on as well. Another way that you could think about this particular problem is I could have done it kind of really all together. I could have said, well, I know that the centripetal force is equal to the frictional force, okay? I know that the centripetal force is mv squared over r. I know that the frictional force is the coefficient of friction times the normal force, which is the same as the mass times the gravity. At that point, the m's cancel out, and then I'm going to be left with v squared over r equals the coefficient of friction times gravity. And in place of actually solving for centripetal force in terms of m, I could have simplified my equations this way first, and then just use this equation down at the bottom to go ahead and solve for velocity. So again, this too is a technique that you could use. This simplifies it a little bit. Set the two equations equal to each other from the beginning. Notice that the mass cancels out, and then take the remainder of the variables and plug in for those. So a couple of different ways to think about that problem. It's basically the same thing no matter which direction you go. But regardless, the mass is going to cancel out, and that's what makes it possible to solve that.